Okay, before we start looking at binary numbers, I want to talk a little bit about the decimal number system, the one that you and I use every day for counting. I've got this diagram set up here, and I'll describe it real briefly. First, because we're dealing with base 10, then all of the numbers, all of the values are based on a 10-digit alphabet. So there are 10 digits in the alphabet that I use to create every number. Those digits are 0 through 9. Add them up, you've got 10. In this first rightmost position, our base, 10, is raised to the 0 power. Now this is a rule of math that you just have to accept. Anything to the 0 power is equal to 1. As we move to the left with each place value, the exponent goes up by 1, and so 10 to the first power in this position means this is the tens place, the ones place, the tens place. You remember this from school many years ago. 10 to the second power, the hundreds place, and 10 to the third power, the thousands place. So what does all this mean, and how does it relate to binary? Well, check it out. In this first hangman slot, this first position, I can put one digit, 0. I can put 1, 2, 3, all the way up to 9. And the value that I end up with is whatever's in that position, 9, times the weight of this position, 1. 9 times 1 is 9. Add everything up across here. My value is 9. Not too exciting yet, huh? Okay, let's make it a little more exciting. In this position, again, I can go 0 through 9 in this position. So if I have a number like 4, 4 times 10 is 40, plus 9 is 49. Wow, I know, still not very exciting. If I have a number like 7, if I put, 6 in this position, the digit 6, that's 6 times 10 to the second power, or 6 times 100, 600, plus 4 times 10, 40, plus 9 times 1, 9, add them all together, 649. If you can understand how that works, and how you add after multiplying, you multiply this digit times this weight, which is another way of saying this digit times the base raised to this power. 6 times the weight of 100, plus 4 times the weight of 10, plus 9 times the weight of 1. If you can get that figured out and see that that's how we arrive at the value of 649 in base 10, then binary is going to be a cinch. So let's shift gears and take a look at this same type of diagram, only with binary numbers base 2. Now that you have a good understanding of the decimal system, base 10, let's take a look at the binary system, base 2. Base 2 means that our numbering system is based on 2 digits in the alphabet. Each position can contain one of 2 possible digits, 0 or 1. 2 digits. Our base, 2, raised to the 0 power, as we discovered earlier, anything to the 0 power is 1. Our base 2, raised to the first power, is 2. 2 to the second power is 4. And the lovely thing about base 2 is that as the exponent increases by 1 with each position to the left, the weight of that position merely doubles. So 2 to the third is the 8's position, 2 to the fourth, the 16's position, 2 to the fifth, the 32's position, 2 to the sixth, the 64's position, and 2 to the 7th, the 128's position. Count up the number of positions I've got here. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 digits in the binary numbering system, or 8 binary digits. Binary digit, we contract down to bit. BI from binary, T from digit. If we take these 8 bits and treat them as one unit, that unit of measure is the byte. So let's see what happens. If I put a 1 in this first position, oh wow, 2 to the 0 power times 1 is 1. I'm getting excited about this. What about 1, 0? 2 to the first power is 2. 2 times 1 is 2, plus 0 is 2. Okay, still not terribly exciting. What about 1, 1? 2 to the 1, 2 to the first power, that's 2, times that 1, 2. 1 in this position, 1, 2 plus 1 is 3. Okay, still nothing, huh? What about this? 1, 0, 0. Why is that 4? Well, it's 4 because we have 1 in the 4's position, or the position that is 2 to the second power, and 1 times that weight, 4, is 4. Well, what about 1, 1, 0? Why is that 6? Because 1 times 2 to the second power plus 1 times 2 to the first power plus 0 times 2 to the 0 power, 4 plus 2 plus 0 is 6. Let's get a little more challenging. What if I've got a crazy number like 0, 1, 1, 0, 0, 1, 0, 1? Why is that 101? Well, here's why. Because 2 to the 0 power, or 1, times 1 plus 0 times 2 plus 1 times 4 plus 0 times 8 plus 0 times 16 plus 1 times 32 plus 1 times 64, 64 plus 32 plus 0 plus 0 plus 4 plus 0 plus 1, 101, or 101. If I add 1 in this position, it's going to have a very significant impact on the value of this whole number, because it's going to change it by a factor of 128. And that makes my number 229. So the bit in this position is most significant. The bit in this position is least significant. Watch the change it makes when this rolls from a 1 down to a 0. We went from 229 to 228. That's not a very significant change. But if this goes from a 1 to a 0, we go from 228 to 100. So this is the most significant bit, or MSB, most significant bit. And the rightmost is the least significant bit, or LSB. In the previous example, we looked at how to determine what the value of a number in base 2 is in base 10, essentially converting a binary number to a decimal number, converting base 2 to base 10. In this portion, let's go the other direction. Let's take a decimal number, a number that's in base 10, and convert it into binary. Our first example I'm going to use is 151. 151. I like to think of this as one of those games from The Price is Right. Do you remember the cliffhanger game? The one with that little yodeling guy? Oh, come on, think. I'm sure you've seen it on television. Well, I like to think of things like that as I work out these problems of converting base 10 to base 2. And here's why. As you look along the weights down here for the place values, compare the highest weight to the number that you are trying to convert. And just like in Price is Right, you try to get the highest bid without going over, we are going to try to bid as high as we can without going over. And so I yodel all the way up and say the highest number that will divide evenly into my base 10 decimal number is 128. And there's exactly one of those. 128 subtracted from 151 is 23. So now I keep going. There's no 64 in 23. There's no 32 in 23. But 16 will divide into 23 one time, with 7 left over. Will 8 go into 7? No. So that's a 0. Will 4 go into 7? Yes, there's 1 in there. That leaves us 3. There's a 2. That leaves us 1. And there's a 1. Add them all up. 151. Let's try another example. What about 63? Let me clear things out right here. $63. If I take my little yodeler and yodel my way up through here to try to find what's the highest number I could bid without going over. If I bid 128, I've gone over. If I bid 64, I've gone over. But if I bid 32, that will fit. 32 will divide into 64 one time, and that leaves me 31 as a remainder. 16 will go into 31 one time, and that leaves 15 as a remainder. 8 will go into 15 one time, and that leaves us 7 as a remainder. 4 will go into 7 one time, leaving 3 as a remainder. 2 goes into 3 one time. Oops. 2 goes into 3 one time, with 1 as a remainder, and there's the 1. Add them all up. 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 63.